Hello and welcome back. In this video, I'll continue to introduce features and basic aspects of ANSYS HFSS for the design and analysis of antennas. Today we will perform a simulation on a pre-made planar spiral antenna design sourced from the HFSS antenna toolkit. We'll discuss how a simulation is set up, what components are necessary, and how to view and export the results. I'll assume that by this point you are familiar with opening the application, creating a new project and an HFSS design, and navigating the model hierarchies with a good degree of familiarity. So without any further delay, let's go ahead and get started. The first thing you'll want to do after opening the electronics desktop application is go to View and enable ACT extensions. This window will open up. You'll want to hit Launch Wizards and then hit HFSS Antenna Toolkit. This will allow you to open the toolkit and insert antennas that HFSS has preloaded, designed, and you can customize to your desired characteristics. You can edit and insert anything from bow ties to dipoles, horn antennas, monopoles, and we'll be focusing on planar Archimedean spiral antennas. If you click on this, you'll see that we have settings we can edit for this spiral, like the low and high frequency. Let's go ahead and set that from 2 to 8 gigahertz. And then you have underneath that antenna dimensions. The antenna dimensions of a spiral are dependent on the frequency bounds, and so when we hit synthesis, we'll see that these change and adjust according to our desired range from 2 to 8 gigahertz. The number of points per turn on the antenna determines how smooth the curves are, which are shown in this little image here. The more points per turn, the smoother the curve will be, which means more accurate and realistic simulation results, but that comes at the cost of simulation time. We'll say 50 points per turn as a decent trade-off. Once we're happy with our antenna dimensions and setup, we can go ahead and click Finish. This will insert a planar Archimedean spiral into the software. We can close ACT extensions and maximize this viewing window to see our planar spiral antenna, which has been added in. So over here, you can see that a new project and an HFSS design have been created, and many new features have been added to this hierarchy here. And then in the model hierarchy, we can see correspondingly the different elements of the design have been placed in for us. So at this point, you can go ahead and set up your simulation and run a few simulations to view the results and performance of this antenna. But before we do that, we'll go ahead and go through some of the different features that have been added in that you might have seen now for the first time. The first thing we'll look at is the boundaries. There's this boundary called antenna metal. This essentially shows you that the two arms of the antenna are perfect E type, which stands for perfect electrical conductor. This means that the antenna arms have infinite conductivity and do not cause losses in the system. This allows for the simulation analysis of your antenna without respect to copper losses or conductor losses. Underneath that, we have excitations. This is the first lumped port, hence the name 1. If we open that, we can see that this is a lumped port, essentially the simplest type of input port for an antenna, and it has an impedance of 50 ohms. We know that most antennas don't have an input impedance of 50 ohms, and so after calculating what it is, you'll want to place that right here. So for instance, if the spiral antenna has an input impedance of 160 ohms, we would write 160 and click OK. Under post-processing, it's important that you select Do Not Renormalize, which will essentially allow the 160 ohms you set to be the impedance of the antenna throughout the simulation. Otherwise, if you hit Renormalize All Elements, and you go down and open this terminal right here, you'll see that this renormalizing impedance, which is by default set to 50 ohms, will actually override the input impedance of the lumped port that you had set earlier, and your S parameter results will be off from what you expect. The reason we set the lumped port impedance to be matched to what the antenna's input impedance is so that you can determine the performance of your antenna without respect to the quality of the matching network, which is usually designed separately from the antenna itself. Underneath analysis, you can see that ATK solution has been set up with two sweeps, FF sweep or far field sweep. If we open that, we'll show you a linear count from 2 GHz with 3 points, and it is in discrete format of a sweep type. What this means is that HFSS will simulate the antenna at 2 GHz, 5 GHz, and 8 GHz, and this will allow us to see far field results and radiation patterns at 3 distinct frequencies, rather than at every quarter gigahertz or smaller division, which is usually not important when looking simply at far field results. And we can see that the save fields at all frequencies option has been selected. If you don't select this, you won't have far field data to see. Underneath that is an S-param sweep, which, as you might have guessed, sweeps a broader range of frequencies and yields the S-parameter results. And this is an interpolating type of sweep, which is less accurate than discrete, but usually faster in simulation time. Hence why 100 points has been chosen between 2 and 8 GHz. And the 3D field save options, save fields button is not selected because this is a merely S-parameter based simulation. Underneath the results category, we can see a variety of reports have been added. So you can see far field 3D gain RHCP, so the right-hand circularly polarized gain can be plotted here. This is the left-hand circularly polarized gain, cross polarization, and then variance of those. At the very bottom, we see the return loss and input impedance reports are also plotted. These are currently gray, but once we run a simulation, these will be colored, and then you can access the data and plot it visually. Also important are these radiation setups. You have a variety of different 3D definitions. These essentially tell HFSS at what phi and theta angles to simulate the antenna in the far field at. Currently for the 3D radiation sphere setup, we have phi swept from minus 180 to 180 degrees in step size of 2 degrees, and the theta angle from 0 to 180 degrees also in step sizes of 2. This design has come preloaded with a couple of radiation sphere setups that will allow us to quickly display data once it's been simulated in the 3D format and 2D format. So one thing you'll always want to do before running a simulation is make sure that all the various elements and necessary components are there. We have our conducting elements, we have a lumped port, and we know that the excitation has our best guess impedance, let's say 160 ohms. We are not renormalizing this impedance. We have an analysis setup and a specific sweep for what we want to see. And we have reports already created, although these are not necessary to start the simulation. But before starting, we'll do one more thing. Hit HFSS and click validation check. This will ensure there are no errors that when we start the simulation will cause it to stop. So now with this ready, we can go ahead and right click on far field sweep and hit analyze. This will show us the far field performance of the antenna at 3 discrete frequency points. And so I'll come back when this simulation has finished. Now that the simulation has ended, we can see some messages have popped up in this little window, including the normal completion of simulation on server message. This indicates that our simulation was successful and we can go ahead and view the data. So you can see that a few of the results reports have now been colored in, they're no longer gray. And when we click on them, we can see data has been plotted here in a 3D polar format. We have the right-hand circularly polarized gain plotted in dB. If we open this, we can see that it uses the last adaptive sweep, but we want the far field sweep. So all that this means is that the frequency was 8 gigahertz, and that's what's being shown. We want to use any of the 3 frequency points that were simulated, so 2, 5, and 8. Let's go ahead and select 5 just for the time being. And the geometry, these are the radiation setups that are lower on the hierarchy. This shows the sweep of phi and theta that can be plotted. So if we were to keep it at this 3D geometry and apply the trace, we would see the 3D radiation pattern at 5 gigahertz. And this can be spun around just like the model using the same keys and zoom features and Control D to fit it to the screen. If we were to change this to, let's say, the elevation geometry, we would see a cut of this very different since the angles of phi and theta have now been limited. And if we were to change it again to, say, the azimuth geometry and apply the trace, we would see only the cut in the 90-degree theta plane. And so quite a bit of options. Not every plot is suitable for every geometry. Of course, these 3D far-field plots work best with full ranges in 3D geometries. We can also see a 2D polar plot. This is both the right hand and left hand circularly polarized gains. The red and blue, which you can highlight by clicking on these legend labels here, are the right hand circularly polarized gain, and then the green and orange colored curves are the left hand circularly polarized gain. You can see a good degree of separation between the two. And we click on either of these, and we see that it's also in the last adaptive sweep. We can go ahead and change that. If we go over to families, we know that the primary sweep is theta. So this is the gain plotted across different values of theta. And that's what's on this radial plot axis here. Under families, we see the other two variables that we can pick. It's currently using all variants of phi. Let's say we want 0 degrees and we assume homogeneity between the different angles and we want 5 gigahertz. We can change that and hit apply trace. And now we have the radiation pattern at phi equals 0 and across theta at 5 gigahertz, which looks very much like a cut of the 3D image we saw prior. And lastly, below that, we have stacked rectangular plots of the different gains. So right hand, left hand, different values of phi, and then down below a little further, we have different frequencies for each variation, frequency and angle of phi. So if you wanted to export this data, you could simply right-click on any of the result reports. So for instance, if I wanted to export all of these plots into, let's say, a text file and post-process them and plot them elsewhere, you could right-click and hit export. This will allow you to save it in whatever file name and whatever format available. I'd recommend a CSV file. And an important tip that you might want to remember when exporting multiple plots or multiple curves on the same result report is to select this Use Separate Columns for Curves option. If not, the separate curves will be appended to the end of so vertically the bottom in a CSV file, rather than have separate curves where there's the independent axis, in this case theta, or in other plots frequency, and then to the right separate curves, separate columns for all of the different variants plotted here. You won't need to do this when there's a single variable such as the input impedance across frequency, but this will be useful in reports like this, or for instance 2D polar plot reports like this one. We would want to export and use separate columns for curves. And you can see that the option is selected and remembered between reports, so you must only do this once. So this far-field sweep didn't save all of the data for all of the result reports. There is an S-parameter sweep, which we can run and simulate and then access the return loss and input impedance. So we'll go ahead and do that. We'll right-click and analyze that, and then come back when that simulation is finished. All right, now that our simulation is finished, we can go ahead and look at the data that it has produced. So the first thing we'll look at, let's say, is the return loss. So we can see that it's plotted in negative values, which indicates that the tidal return loss is a bit of a misnomer. This is rather truly the magnitude of the input reflection coefficient of the antenna. Nevertheless, it's reasonably well matched across frequency, and this is probably due to the fact that the input impedance of the antenna is somewhat close to the impedance that we set the input port to, namely 160 ohms. If we wanted to fine tune this so that what we see in the return loss is truly due to the antenna itself and not caused by the mismatch between the input port and the antenna terminals, we'd want to see the input impedance of the antenna across frequency and, to our best judgment, select a value for that lumped port. So we can go ahead and do that, but this report is the input impedance plotted on the Smith chart. And we can't exactly tell what the impedance is because we don't know at which frequencies these points are plotted. This could be 2 GHz or this could be 8 GHz. We don't know yet. One way to find out is through markers. If you right click and hit marker and then add marker and drag your cursor over the line, you can see that you can plot points along the line, and then a legend will be generated giving information about the marker you just placed. And from there, you can see the different values of that input impedance at, say, 3 and 6 GHz, including the angle, magnitude, and other values. Now, we don't see an input impedance across frequency report here, but we can make one of our own. If we go to the results ribbon and hit terminal solution data report, and then go to 2D, this will open a rectangular plot generation window. We can add our own input impedance plot as desired. Under solution, we want to make sure that we're taking data from the S parameter sweep results file. And we want to make sure that under category, we have terminal Z parameter. This is where the input impedance is located. And we don't want to see this in 20 times the dB. We want to see the real and imaginary part. We can go ahead and click new report, close this, and see that the real part plotted in red stabilizes to around 150 ohms at the higher frequencies. And since our guess was 160 ohms, this indicates reasonably well matching between the two, hence the decent return loss that we saw previously, or rather input reflection coefficient. Likewise, the imaginary part is centered around 0, so we don't have to add an imaginary component to our to the input impedance of that lumped port. So there are still a variety of different features that you can plot, and there are very different reports that you can generate that we haven't seen yet. I recommend going through the different categories and exploring what options there are. I'll go over one more that's pretty important. Under the far fields report and under the 2D type of plot, you have the option to plot the axial ratio in dB. And of course, you'll want to do this across a primary sweep of frequency. Now, of course, this far field sweep, which saves the data necessary to generate the axial ratio value, was done at 3 discrete frequency points, and so there won't be enough information to create a smooth curve across frequency. And in future videos, I'll show you how to set this up so that more points are added and you can be able to see this value and judge the quality of your antenna design based on that. One important thing that some of these new reports, when you generate them, have, which is sort of a tedious quality to remember to undo, is under families. We can see that there are 16,471 available families. What this means is that although the axial ratio is going to be plotted against frequency, it is going to be plotted with a variety of combinations of phi and theta across frequency as well. And so that means the axial ratio at phi equals 0 and theta equals 0 will be plotted across frequency, and then phi equals 2, theta equals 0, and so on and so forth. You want to make sure that these variables are selected such that a single point is chosen and not all values, or else when you click new report, HFSS will attempt to generate 16,000 plots, which will be, it will take up a lot of time and it may crash the software as this is a massive amount of data. And so sometimes these plots by default have families set to all variables, all values of variables, and you'll need to change that. And so if you generate this report, we'll see a piecewise linear sort of line here because there are only 3 points. But we can see that at least at 5 GHz, our antenna is circularly polarized as the axial ratio is close to 0. So with that being said, go ahead and, as I mentioned, explore the different results, the different ways to plot the data, and try exporting some of the data yourself to get familiar with simple simulations and viewing results. And in future videos, we'll learn how to set all this up ourselves and customize it to our specific needs and requirements. Thank you.